All right, so we are starting with electric potential, Unit 8 today. We're going to discuss potential energy. We're going to review the idea of potential energy in general. Then we'll discuss the definition of electric potential, which is slightly different from potential energy. Introduce the unit of the volt, and then talk about the potential in a uniform field. So, potential energy. All right, potential energy. We've dealt with two types so far. We've had gravity, okay, and we've dealt with springs. Okay, but for all of them, we've discovered that as we that the potential energy is the potential to do work. It is the ability to do work, and if we exert a force, so that work is a force over a distance. But if we find that because work is defined as increasing the kinetic energy of something, okay, and if we use our potential to do the work, okay, we increase an object's kinetic energy, but at the same time, in order for it to use that potential decreases. Okay, when we use our potential to do work, our potential decreases. And so we have our change in our potential has been equal to, okay, our conservative force, okay, dot ds, well, which is the path. And our force, our conservative force close to the Earth is, mg. Okay, but there's this cosine term in there, right? That we've dealt with, and this is negative, right? This is a negative integral. That cosine term makes our when we have that cosine, when we have that dot in there, it makes our energy considerations path independent, and so it doesn't really matter the path by which we adjust our potential energy, as long as, for example, in gravity, as long as it's only the component that is directed towards the center of your massive object, rather than along path. So if you're in orbit around a massive object, you're not changing your potential energy very much at all. Okay, well, the same thing applies for electricity, because what is our electric force? Our electric force equals, well, there's the k q1 q2 over r squared, which is the Coulomb's law, but it also equals our charge times our electric field. All right, and so if we have our potential energy, delta U equals, and I put the that's messy, so that's not, no, fine. Yes, I know, I have to go pick up my daughter.
It's calm.
Okay. Okay, so we're going to have the same situation, that our potential energy is going to decrease as the electric force moves an object along in its along its path. Okay, so it's exactly the same equation, but we can throw this now in here, and we get delta U equals negative integral of q e dot ds. Okay, but if q is our test charge, and we can divide this whole thing by q, and we get, if we divide our potential energy by q, we get negative integral of E dot ds. And this is defined as the change in our electric potential. Okay, so this is a delta V. This is a V. This is in units of joules per coulomb. C-O-U-L-O-M-B, joules per coulomb. And this 1 joule per coulomb is defined as a volt. okay, which also has the abbreviation V. It is the only one, as far as I can think, that the variable of the variable of the unit here, the variable of the quantity, is the same letter as the unit of the quantity. Yeah. So it will not be an unusual thing to see V equals 2V.
Is that small?
You will see that.
Is it same capital?
It is highly, yes, they're both capital, and it is highly recommended that you distinguish between the two. Don't lose track of this, and it's easy to make that mistake. So, there are things in the past. Right. There are. No, it means you divide by 0. I've seen that before. Okay. Nice out, Omar. Okay. So, what some people do, or actually when we get into circuits and that sort of thing, when we start, we'll have induced voltage. We'll start getting a cursive E, okay, and this stands for EMF, which is an electromotive force, which is the same thing as potential, but we'll get there another time. Some people do a big old script V equals 2V. I won't. Okay, I might do this. I might just make the unit smaller and the variable bigger, but it's a style thing. Okay. Now, with this in mind, with this confusing part here in mind, we have these terms here. New vocabulary. We have potential. We have electric. Potential. And we have voltage. These terms are interchangeable. These terms are interchangeable. Potential, electric potential, voltage, they all mean the same thing. They're all referring to the same quantity. They're all referring to the same concept. Okay, so let us then come up with some point charges. Okay, here's our point charges. All right. Our point charges are exerting a field in all directions. All right, and then we have a test charge. A test charge enters the field, and he is here. All right. And then this has, and we can, is it R1 distance away? Okay, and so he has a particular amount of potential energy. Wait, hold on. I want to make sure I got my notes right. Oh, well, he's experiencing, okay, right. He's experiencing a field right here. E equals KQ over R squared in the R hat direction. Yep. Okay, so he experiences an electric field in the KQ over R squared in the R hat direction. All right, so we start using this. Oh, and we're going to move him. Right there. Okay, to a new place where we have R2. Okay, right there. And he will have a, this is where we move him to. So, according to our equation over here, That I can't get the whole thing on screen unless I rotate. All right, so our change in potential is going to equal this. So we get our delta U over Q from our potential down here equals negative integral from R1 to R2 of K Q. This is Q. This is Q up here, KQ over R squared R hat dot ds. All right, so what do we get with this? Well, the dot here, ds, in the direction of r is just r hat again, right? R hat dot r hat is 1, essentially. So this just becomes r. You follow that? That the ds, the change in our position in the r hat direction, is just our change in r. Yeah? You guys with me on that? Yeah, no. I'm seeing as we move through here, what is the change in the r hat direction? How much closer do we get? Okay, it's just dr, right? That this distance here, okay, this distance is our total change in r. So we're going to get K1, Q2, or K, right, KQ over R squared dr. Well, this is a constant, so we're going to get KQ, and then we're left with and what does this become? Our delta voltage equals K Q negative R is minus 1 over minus 1 from R1 to R2. That negative hits with that positive. And so now we have yeah? Does it look familiar? Oh, I'm sorry, we got down. All right. So we're here. Evaluated from R2 and R1. But just like with our gravitational potential, we talked about what was our gravitational potential at an infinite distance away from the Earth? 0, right? We assigned that infinitely far away equaled 0. Same thing here. Okay, so what happens if we're just worried about the potential at a particular place? So we imagine we went from a really far distance away and bring it to this place. This goes away. I'm sorry. Goes to 0 as R1 approaches infinity. And so this becomes our potential of a point charge, is V equals KQ over R squared. I'm sorry, no, KQ over R. Sorry, no, my bad. Over R2, or just its distance. Nick. No, it is not. This negative here cancels with this negative in our integral to make it positive. It is not negative. How's it different from this? For gravity, yes, but gravity is an attractive force. We're talking about a positive point charge in a positive positive electric field.
Pushing away, right?
Yeah, it's pushing away.
then you have
This force is pushing. The potential, shh, guys, the potential is pushing away from the center, which gives it a positive potential the closer we're getting.
Okay.
Can I say that?
That makes sense.
The closer we get to the charge, the more it pushes away. Therefore, it's a greater potential the closer we get, as opposed to a greater potential the further away we get for a gravitational pull. Okay. Any real quick addendum to this? We've got a little bit of time on this. In a uniform field, okay, in a uniform field, guys. Oh, wait, okay, one other thing. Yeah. What happens if I move this particle this way, keeping the same distance?
Same potential.
Okay, there is no change in potential.
Yeah.
Okay, there's no change. If it stays the same distance away, there's no change in potential. So if you start thinking components, if you start thinking, d theta and dr, all the side to side stuff doesn't matter, right? The only thing that matters is to and from. Okay. I've got like 3 minutes. So. Okay. Now, uniform field. Let's say we've got a charge R1 and we move it to some other place. Okay, R2. Our delta R is that. That's our delta R vector. Right? So our voltage equals negative integral E dot ds. Okay. But dot ds we know is delta R, right? Okay, if this is the same, then our ds is we're just worried about delta R because everything else is either along, if the two components are either along or perpendicular to the field. If it's perpendicular to the field, it doesn't matter. If it's along the field, then it matters. So this becomes negative E dot delta R, which becomes negative E delta R cosine theta, with that being theta, the angle that R makes with the electric field. Okay.
Angle?
Okay. Yeah. So the cosine theta is, if R is in this direction, this is the angle that's making with the electric field. Okay. Or you could use either side, but then you have to pay attention to your negatives. Okay, that's it for intro to potential.